Welcome to Lecture 8, Part 2. In this part, we're going to be continuing our discussion of working memory capacity and how to measure it in animals. We started this discussion last time where we talked about two methods, right? The radial arm method and the delayed match to sample method. We saw that sometimes they give you different estimates of the duration of working memory, and we also explained why. In this part, we're going to be discussing a third method for assessing working memory capacity, the expectancy-violation method, and I'm also going to discuss an application of it in the study of Portia spiders. But let's start by discussing the expectancy-violation method in general. The way that it works is that an animal observes a scene, and the scene consists of a particular object. And after a certain amount of time, the object disappears behind a screen, and it disappears for a certain amount of time. And then while it disappears, an alteration is made to the object, or it is left the same. Right? And then the object reappears, and the experimenters measure some behavior on the part of the animal. And in particular, what they're interested in doing is comparing behavior for the altered and the unaltered conditions. And the reason for this is because if the behavior is different when the scene had been altered in some way, what this means is that the animal has been storing in working memory the original scene and is comparing it to the present scene. If there's no difference between the two conditions, altered and unaltered, it means there is no such comparison taking place. So nothing is being stored in working memory. Okay, so if the behavior is different following an altered scene than an unaltered scene, the animal has detected a mismatch between the two scenes. Right, there's a mismatch between the current scene and what's represented in working memory. And this is violating an expectation, right? So it implies that an object was stored, or a scene was stored in working memory, and the animal is being surprised by what he is currently seeing. But if the behavior following the altered scene is the same as the unaltered scene, it suggests that there is no original scene being stored in working memory. So as I said, this has been used to study working memory in Portia spiders, and the study I want to talk about is by Cross and Jackson from 2014. And we know that Portia spiders like to hunt other spiders, and when they do so, they classify their prey by what type of spider it is. And we know that because what they do is they approach the web of the resident spider and they perform a unique vibration pattern to try to get the spider to come to it, and then they attack it. But the pattern of vibration on the web depends on the kind of spider that they're attacking. And their ability to categorize spiders by type is facilitated by their very good vision. So the question that Cross and Jackson were addressing was whether Africana spiders load into working memory accurate representations of particular types of spiders, right? Spiders that they hunt in their natural environment. And in their study, they used lures of 4 prey species of spiders, and they did so using an expectancy-violation paradigm. So what they manipulated was whether the type of spider changes. Right? Does the type of spider change or remain the same from the first presentation to the second presentation? And they also examined or manipulated whether the orientation of the spiders remained the same or varied from the first presentation to the second presentation. So they wanted to test 2 factors that might play a role in their expectations and whether or not they're violated. The type of spider and the orientation of the spider. The orientation referring to the direction that the spider is facing. Right, so and the behavior that they're interested in was the tendency to leap at the prey spiders. is the tendency to leap at the prey spider on the second presentation affected by the type of spider that reappears, and is it affected by the orientation in which the spider appears? So the setup for the experiment looks something like this. At the top we can see that there's a tube, and in the tube, that's where Portia is transported to the experiment. So from the tube, she can go up a ramp where she can get a good look at the lure that's presented in the window. So the lure is presented for a certain amount of time, and then the lure is pulled back, and then a shutter comes down. And while the lure is pulled back, the lure is either altered in some way, either by changing the type of spider or by changing the orientation, or holding those factors constant. And then the shutter comes back up, and then the lure is inserted right out the window again so that Portia can see it. All right, so let's review the procedure again. Portia is held in a tube, and at the start of a trial, the tube is unplugged, the shutter is raised, and the lure is moved forward towards the window. And as I said, the lures are dead spiders, but they're put in a position so they look like they're alive. So the Portia spiders walked up the ramp, and they were allowed to look at the lure for 30 seconds. And then at the end of those 30 seconds, the shutter came down, and the lure was either changed or left the same. And that the shutter was remained closed for 90 seconds. And then after the 90 seconds, the shutter was raised again, and the lure was once again moved out, this time so that it's in front of the window. And the reason why it was pushed out farther was so that Portia would be easily able to jump at it if it so desired. And the Portia spiders were allowed up to 5 minutes in order to leap at the lures. And what they recorded, the main dependent variable in this study, is the likelihood of them attacking the prey spiders. And there were two main conditions in this study. Right? In the first condition, they manipulated the type of prey. And in particular, the type of prey was either the same at the beginning and when the prey reappears, or it was different. And in this condition, the actual orientation, the direction that a spider is facing, is held constant at both times. In the second condition, the same prey is presented at both times, right? So it's always constant, but what they manipulated was whether the orientation of the prey stayed the same or was different. So let's look at the results for the first condition. In this one, where the prey is manipulated and the orientation is constant, there was two subconditions, right? The control trials and the experimental trials. In the control trials, the same spider was presented at the beginning and the end, right? So when it reappears, it's the same spider as at the beginning. Or in the experimental trials, the spiders were different at the beginning and at the end of the trial. And what we can see is that the likelihood of Portia attacking the prey was much higher, overwhelmingly higher, when it was the same spider presented at the beginning of the trial and when it reappears. Right? When it was a different spider, they were much less likely to attack when the spider reappears. So what this suggests is that they're storing in working memory for the duration of the trial a representation of the spider that they had seen at the beginning. And the reason why they don't attack in the experimental trials is because they're surprised at seeing a prey that they didn't expect. Okay, so the Africana spiders are more likely to attack if the spider is the same at the beginning and at the end of a trial than if it's different, suggesting that they've stored in working memory a representation of the object that they saw at the beginning. In the second conditions, right, the orientation of the spider, right, the direction in which it's facing was varied or manipulated, but the actual prey, the type of spider, was held constant. So it was always the same at the beginning and at the end. And in the control trials, the spider was in the same orientation at the beginning and the end, and in the experimental trials, the orientation of the spider was different at the beginning and at the end. And they found that this manipulation made no difference. Right? For this one, they were just as likely to attack the spider if it was in a different orientation as if it was in the same orientation. All right, so let's summarize the experiment. Right? When the shutter is lifted, the Portia spiders could determine whether the type of prey that's seen is the same or different as what they had seen in the earlier part of the trial. Right? So they could tell whether or not it's the same spider that's presented or whether it's a different spider. And this affected their likelihood of jumping, as I said, and attacking the spider. And what this shows is that they can hold this information in working memory for at least 90 seconds. Orientation, however, didn't seem to affect the likelihood of attacking, as I said. So why would seeing the spider in a different orientation not affect the likelihood of jumping? Because in the real world, right, outside the lab, spiders changing orientation is something that happens all the time. So it's not going to violate any expectations on the part of Portia. All right, so we've discussed the expectancy-violation method of examining the duration of working memory, and we applied it in the case of Portia spiders. But the astute student will notice that the amount of time that the information was held in working memory was always the same, 90 seconds. But this doesn't tell you the actual duration of Portia's working memory. Right? It tells you at the very least they can hold information for up to 90 seconds. So to figure out the actual full duration of working memory on the part of Portia or any other animal, what you would have to do is you would have to manipulate the amount of time that occurs, or the amount of time between when the shutter comes down and when the shutter comes back up. Right? In this case, it was 90 seconds. So what you'd have to do, for example, is push it out to a minute and 15 seconds and a minute and a half and so on, to try to see, well, at what point does performance between the two conditions the same or different? At what point does it no longer make a difference? And that would tell you the full duration of working memory. Okay, so to get a complete assessment of duration, we would need to vary the amount of time that passes between the two presentations, rather than holding it constant, as in this experiment. All right, so that's it for this lecture on working memory. In the next lectures, what we'll be exploring is long-term memory.